Hi, now we are going to start describing magnetic phenomena. So this is the second half of that course, the electromagnetism course. But unlike electric fields, the topic of magnetic fields are a little bit more complicated than the electric fields. And that's basically both physically and mathematically. And there are several reasons for that. And we are going to describe some of these reasons, but expect some difficulty in there. So in the next 1 month or so, we are going to see different aspects of magnetism. So, of course, I'm going to start introducing the magnetic phenomena by first describing the magnetic force, just as we have done with the electric fields. So let's remember again what how we describe the electric force. The electric force is the force between two charges. So there are two charges that are interacting, they are applying forces to each other. And we just first described this electric force. So that's the famous Coulomb's law. Okay. So I'm going to do the same thing for the magnetic force. So this time, I'm going to claim that if two charges are moving, both of them are moving, then in addition to the electric force that they apply to each other, there is an additional force that these moving charges apply to each other. So we are going to call that force as the magnetic force. So as a result, this is the essential idea. Magnetic force is the force between two moving charges. But of course, two moving charges apply also the electric force to each other. But in addition to that, they apply another force which is specific to the moving charges. So let me also show them in the vector language. So in the case of electric force, we know that by Coulomb's law, they either attract or repel each other. So I'm writing the magnitude in here. I'm just describing only the case where these are like charges, so that there's a repulsion in here. But there's an electric force when there are two charges. So it doesn't matter whether the charges are moving or not. So this electric force is there. So there's an electric force in here, also in that case too. But in addition to that, when these charges are moving, there's an additional magnetic force. I'm going to show them like that. So there's also an additional force in here, which we call as the magnetic force. So I also draw both forces again. According to the Newton's third law, they have to be equal and opposite. Okay. Essentially, therefore, two charges can interact by applying two different kinds of forces. There's an electric force and a magnetic force, but the magnetic force is only applied when both charges are moving. You can think of it like that, right? We can also, I don't know, we can write down a Coulomb law-like expression for moving charges for the magnetic force, but this is a little bit more complicated mathematically. So instead of that, just as we have done for the electric force case, we introduce the fields now. So again, let's remember the electric field situation. We just said that there's something called the electric field. So that's a real physical entity, right? It's not just our imagination. So electric field really exists. And what we are saying is that a charge interacts with that electric field. So when a charge and a field is present, charge somehow modifies the electric field, and also the electric field applies a force on the charge. So let's remember these. So there are these two aspects of the interaction. So a charge produces an electric field or modifies a already present electric field. We just say that a charge produces an electric field. And when I place a charge inside an electric field, there's a force on it. So the electric field applies a force on a charge. Okay. So let me draw this field this time with a blue color in here. So this charge produces an electric field. Let's call this as E1. And when I place the second charge inside this electric field produced by the first charge, there's a force on it which is given as force on the second charge is equal to the value of the second charge multiplied with the electric field produced by the first one. Right? We are going to do the same thing for the magnetic field. Right? So in that case, we are going to say that the magnetic fields interact with moving charges. Again, there are two aspects of this interaction. A moving charge produces a magnetic field or modifies a magnetic field, right? A moving charge changes the magnetic field, and vice versa. A magnetic field applies a force on a moving charge. Okay, so again, the same two aspects. So this time, let me draw the magnetic fields with a yellow color. So this charge in here, Q1 charge, is going to create a magnetic field that I'm going to show with the B symbol. We are going to talk about magnetic field lines later on. So in any case, so it's going to produce a magnetic field, and the second charge, when it is placed inside a magnetic field, let's say that the field at that location is like that. In that case, depending on the value of that magnetic field, there's a magnetic force applied on it. Okay, so as a result, we are going to describe the interaction between two moving charges as a force which is mediated by the magnetic field, right? It's essentially these two charges are not directly interacting with each other. The charges are only interacting with the electric and magnetic fields. They modify the electric and magnetic fields, and somehow faraway charges sense that modification, and so therefore two charges somehow seem to apply some force to each other. Okay. So that's essentially the idea. So therefore, there are these two questions that we would like to solve, and as scientists, of course. So the one is basically how the magnetic field is modified by the presence of moving charges. So you can think of it like this. I have a moving charge in here, moving like that. And what is the magnetic field produced by that moving charge at this location in space? Right? That's one question. But since we don't know much about the magnetic fields, probably we need to postpone this question. And the second question is this. There is a magnetic field, and I place a moving charge inside. What is the force on it? And so there's a moving charge in here, and there's a magnetic field in here. So there should be a force on it. There is a magnetic force, so that's the magnetic force. We would like to write down the expression. So these are, of course, questions about the same physical phenomena. It's the interaction between a moving charge and the magnetic field, but we just investigate them on separate chapters. So we first start with, in chapter 27, with the force question. What is the force on a moving charge inside a magnetic field? And then in the next chapter, we are going to discuss how we can compute the magnetic field produced by a moving charge. Okay. So as a result, we are going to start with the force expression. But let's again remind you that in that case, the basic force expression has to be written for force applied on a moving charge. But there's also a common situation that we meet. It's basically the currents inside a current carrying wire. There are many charge carriers in here which are moving inside the wire. So therefore, there has to be a magnetic force on the wires as well. So as a result, we are going to see this expression for both moving charges and the currents. So as a result, we are going to see two different force expressions. But since a moving charge is more fundamental, I'm going to start with the force expression for the moving charge. All right. So when I write down the force expression, of course, this will also give us a possible definition of the magnetic field. Right, let's just draw the situation here. I have a point charge in here with a charge little q. It is moving like that. This has a velocity v, and there's a magnetic field. So let me try to draw all the magnetic fields with the yellow color. There's a magnetic field at the location of the charge. Again, we are going to assume that B is a field, so therefore it has a different value at different locations of space. So that's the magnetic field. So when there's a point particle, of course, this particle only feels the effect of the magnetic field at the location it is present. So we still need to define this units of how we measure magnetic field and things like that, but this can only be done after we write down the force expression. So as a result, there is a force on that charge. So that's the magnetic force. So let me write F mag in here. Okay, there's a magnetic force. This force, therefore, has to be a function of the charge, the velocity of the particle, and the magnetic field. All right, you can see how that force may depend on these three quantities. For example, on charge, if the charge is zero, I mean, if this particle has no electric charge, in that case, there should be no interaction. So therefore, we expect that this magnetic force is somehow dependent on that charge. And when the charge is zero, of course, force is zero, probably this force is proportional to the charge, just like the electric force. All right, so similarly for the velocity, if the velocity is zero, we have said that there is no magnetic force. So therefore, this force should also be proportional to the velocity. And similarly for the field, if there is no field, then there should be no force. So the force should depend on all of these three quantities, and the simplest expression that we can write down is the product of all of these three expressions. Okay, so as a result, I'm going to write equality in here and the product of these two. And then we notice that on the right-hand side, I have two vector quantities, velocity and the magnetic field. Somehow I have to multiply them, right? I have to multiply two vectors, and the result should be a vector. So from here, we can see that there is actually only one possible logical choice for the product, and that's the cross product. I'm also going to remind you what the cross product is. So, but let's just finish this thing. So as a result, this force should be expressed like that. There can be some kind of a prefactor in front, like, I don't know, 2 in here, or I don't know, some constant. But whatever they are, I'm going to think that they are going to be absorbed in the definition of the magnetic field. So as a result, we just write down this equation without these prefactors. So as a result, when I write this thing down, I'm also defining what the magnetic field is. So as a result, I can then talk about the units. The units for magnetic field. So you can see that in here it is newtons per coulomb per speed, so it is meters per second. So the units that I should use for expressing the magnetic field should be Newton seconds per coulomb meter. Let's remember that coulombs per second is an ampere, so therefore I can write this thing down as newtons divided by ampere meter. But since this is something that we use a lot, we have a shortened name for it. It is named after Nikola Tesla, since all units named after a person are shown with a capital letter in the shortened form. So we just show the unit by the capital T symbol. Again, let's remember that even though this is named after a person, this is the name of a unit, so therefore we start this with a small letter. Okay, so this is one of the units that we are going to use a lot. But again, this is a derived unit, right? It's derived from Coulomb, or if you want, it is derived from amperes. So, of course, by the end of the semester, we are going to see lots of electromagnetic units, and that's one of the difficulties with the electromagnetism. We have lots of units that we use frequently, but it's kind of hard to see the relationship between them. Okay. So next, let's just remember this cross product. Let me add a page in here. Cross product. Since I have the product of the velocity and the magnetic field, let me draw them. So to express the cross product, that's what I do. We just slide the vectors so that they start from the same point. Theta is the angle between them. And what we do is that in that case, V cross B is a vector which is perpendicular to both of these vectors. So this is V cross B. So this angle is 90 degrees, this angle is 90 degrees. So let me write it down like that. So V cross B is perpendicular to both velocity and the magnetic field. They are perpendicular. But of course, seeing that the V cross B is perpendicular to both of these vectors does not uniquely define the direction. So we have to use the right-hand rule for that purpose. Right-hand rule. Let's remember what the right-hand rule is. So to describe this, I just draw my right hand again. We use the thumb, index finger, and the middle finger. We don't use the last two fingers. They are useless. So what we do is this. We align the first finger, the thumb, along the direction of the first vector. This is V. We align the index finger along the direction of the second vector. And the middle finger, the third finger, gives the direction of the cross product. So this is V cross B. And not the other way around. So to uniquely identify the perpendicular direction to both of these vectors, we use this direction. So you can easily check that if you take the product in the opposite way. So it's B cross V is a vector which is just opposite to V cross B. And this is basically given like that. So it's so as a result, the order is important. So that's one of the things that you should remember. So do not write down the force expression as QB cross V. That's incorrect. And the second thing is, of course, is that the V cross B has a magnitude which is given as the products of the magnitudes. Let me just write down the names of these symbols and then multiply it with the sine of the angle between them. All right. So let's just remember this, but if you have forgotten all about this, I suggest that you refresh your knowledge. All right. So the next thing, again, let's remember the force expression. So force is equal to Q times V cross B. So that's the magnetic force. Right? Just remember that if you want to change the places of these magnetic field and the velocity, you can change it, but don't forget to add a minus sign in front, or just don't deal with these kind of things. So as a result, let me erase this thing as well. So one of the interesting features of that force is that its power is equal to 0. So let me show it like that. So I'm considering a particle in here, which is perhaps moving like that. The force applied on that particle is always perpendicular to the velocity. That's basically the magnetic force. So let me write magnetic force in here. There can be some other forces that act on the particle. There might be an electric force or a gravitational force. Some other forces might still be present, but we are thinking about only the magnetic force in here, right? So as a result, let's say it like this: power of work done by magnetic force. Power is, of course, work done divided by the amount of time that has passed. So work done is basically force, the magnetic force dotted with the displacement. All right, let's remember. So I'm just considering only the magnetic force in here. So therefore, I just use the magnetic force. So that's the work done by the power of the work done by the magnetic force. So let's remember that this is just the velocity. This is the instantaneous power. So in this special case, since force is the cross product of the velocity with something, and the dot product of this thing with velocity is equal to 0, because the dot product of two perpendicular vectors is always equal to 0. So therefore, we have a very interesting conclusion in here. Magnetic forces do not do work. That's strange, because we are going to talk about the energy of the magnetic field. So we are going to say that just like the electric fields, the magnetic fields also have some energy. So they carry energy inside. And so as a result, they can exchange energy with other things. But somehow, for some reason, the magnetic force do not exchange. Let me say it like this. The magnetic field do not directly exchange energy with charges. So only electric fields actually do that. And so as a result, when some of the magnetic energy is transferred to something else, there should be a different mechanism that should be happening there. Okay, so let's just give a simple example in here. Let's say that, for example, we have an electron in here. Let's say that it is released from rest in here. It has just dropped under gravity, of course. It has dropped by a distance h. So as a result, finally it is in here. And I would like to find the speed in here. All right. So let's say that it has reached a distance h. It has went down. In there, of course, there was some kind of a magnetic field. So there is this Earth's magnetic field is also present in here. There's a magnetic field of the Earth. So therefore, this electron is moving only under the effect of the magnetic force and the gravity. And so the question is, what's the final speed in here? So the solution is, of course, is very simple. Since the magnetic force does not do any work, there is only gravitational work in here. So therefore, the final speed should be equal to the value that you would obtain when you use the gravity, right? It's the square root of 2gh, right? Okay, so let's then talk about the typical magnetic field strengths. So we have defined the unit Tesla. In terms of Tesla, what are the typical magnetic fields? Earth's magnetic fields is one of the things that we actually consider a lot, especially when we are doing lab work with magnetic fields. We should always keep in mind that there's also a contribution coming from the Earth's magnetic field. Sometimes you just forget about these. This is about 10 to the minus 4 Tesla. 10 to the minus 4 Tesla is actually a CGS unit. It's called a Gauss. So 1 Gauss is 10 to the minus 4 Tesla. So as a result, a lot of people refer to magnetic field being of the order of a few Gauss. A typical permanent magnet. So there are also different kinds of permanent magnets. We are going to talk about the source of magnetism when we talk about these permanent magnets, but that's later. So typically these are like a Tesla, right? Half a Tesla, right? 0.1 Tesla or something like that, but usually is around 1 Tesla. And of course, if we want a stronger magnetic field, we use electromagnets. So these are large coils, and we pass large currents from these coils. And in that case, we can obtain larger magnetic fields. Typically, you will get like 3 to 4 Tesla with these electromagnets. And of course, in some applications, we need more bigger magnetic field strengths. But the problem is that for electromagnets, you have to pass some large currents from the coils, and because of ohmic it's not actually it's not possible to do that for a continuous for a sufficiently long amount of time. And so as a result, people have developed some solutions for these kind of things. So one of them is the superconducting electromagnets. So superconductivity is a phenomenon where there is no resistance. And so as a result, when there is a current passing through a superconductor, there won't be any ohmic heating. So for these kind of applications, people prefer superconductors, but unfortunately, most of the materials that we know are superconducting at very low temperatures, and there are also some high temperature superconductors, but these are not high relative to us. So even these are superconducting at very low temperatures, much below than room temperature. So that's the main difficulty in here. But if the prices actually is somehow adequate, then in that case people are using these superconductors. So in CERN, for example, they are using superconducting electromagnets which produce a magnetic field of 8.3 Tesla. So we will also talk about the accelerators, why we need magnetic fields in accelerators. So when time comes, we will also talk about these. The largest achievable field strengths with electromagnets. So that's possible, but of course, it just needs a lot of engineering work. They can produce 45 Tesla. So this is basically continuous magnetic fields. So with pulsed magnetic fields, they can reach higher magnetic fields. But usually, of course, on Earth, we cannot pass this kind of a figure, right? But however, in the universe, there are these neutron stars which have huge magnetic fields. So the neutron stars are not ordinary matter, of course. These are composed entirely of neutrons. There are almost no atoms in there, and basically the empty space inside the atoms is not present. So therefore, these are stars. These are objects, let's say, with an extremely high density. So the density is like 10 to the 14 grams per centimeter cube, right? You cannot compare this with anything that you know, actually. And somehow these neutron stars also produce some extremely large magnetic fields. So these are very large, right? Even ordinary atoms cannot be present under the usual conditions and under these huge magnetic fields.